Hi everyone, I'm Alex, and we're going to be talking today about sharding. We'll talk about how sharding is built in the databases world and how it is going to be built in the blockchain world. Let me first introduce myself. I was engineer number one at a company called MemSQL. It's a distributed database. It is used for analytical processing. It is deployed today at a lot of Fortune 500 companies. Goldman Sachs, Akamai, Uber, and there I was employee number one. I was responsible for sharding. So I built the first implementation of sharding. I was driving all consecutive sharding efforts. Before MemSQL, I was at Microsoft, and before Microsoft, I was participating in the ACM-ICPC. ACM-ICPC is a competitive programming event which happens every year. I was a gold medalist there. Then last year I went through Y Combinator, and that company, through a series of pivots, became Near Protocol. So let me quickly introduce Near Protocol. So Near Protocol is a sharded proof-of-stake public blockchain. It is a direct competitor of Ethereum. And the reason why we're building yet another public chain is that there isn't a good project today which will linearly scale as the network grows. So there are multiple projects. You probably, like each of you probably can name like a dozen chains which are being built today. Most of them would scale compared to Ethereum by a couple orders of magnitude, but they all eventually will have some sort of limit with very few exceptions. Ours is sharded, meaning that it will scale linearly with a number of nodes. We also put a huge emphasis on user and developer experience. So on my phone today, I have not a single D app. That is for a reason. They're super hard to use. So we're investing heavily into making them super accessible for public audience, general audience, and also we're investing heavily into making it super simple to develop for Near Protocol. Finally, we have a somewhat unusual team for a blockchain company. There is no famous PhD leading it. It isn't. Everybody in our team is from industry. We have 3 people from MemSQL. Besides myself, there are 2 other people who are responsible for building distributed transaction execution engine. We have 3 ex-Googlers, including 1 person who was building TensorFlow. And among ourselves, we have 4 ICPC gold medals. So it's a ridiculously strong team coming from the industry. Before we start, I would like to understand better the audience. How many people here are actually technical people? Can you raise hands? Sounds upset. How many people understand Ethereum pretty well? Sounds upset. Okay, cool. How many people understand what blockchain is? Okay, good. So I will start with explaining how sharding databases work, but before we get there, let's see why we even care about sharding databases and how is it relevant for blockchain. It is relevant because many people think of blockchain as a distributed ledger, as the entire history of what was happening in that particular blockchain. However, interestingly, the ledger itself is not. It is just the means of security. What people actually care in the blockchain, such as Ethereum, is the present state, right? For example, if it's CryptoKitties, you care about who has kitties today. You don't really care how those kitties were moving before, and you use Ethereum to make changes to state. So you're sending transactions which affect state, which change the state. So effectively, a subset of any modern blockchain is a database, right? So you would not expect a blockchain to be easier to build than a distributed database, right? So let's see how distributed databases were evolving. So we will go back to 2004. Let's say in 2004 you want to build a new service. It could be an online game, social network, you name it. Most likely in 2004, when you develop it, you would have a single instance, MySQL or Postgres. That will be handling all your queries. And then it will all work very well until users start coming and it doesn't scale anymore. So what you will do next, most likely the first thing you will do is you will put memcached in front of it. So you will rewrite your application layer so that it first goes to memcached and only hits the database when it needs to access some cold data. right? When that doesn't work anymore, you will go and start changing some knobs in your database, buy a more expensive server, and when that when that's not sufficient, you will start sharding manually. Now, the question is why you would do all that instead of just deploying a sharded database, because sharded database did not exist. That was 2004. Today is 2018. Probabilistically, you will do some of that as well, right? So there's still not there's no good sharded transactional database. You might use Firebase, or that could be a better idea, or Mongo, but so why is it so hard to build a sharded database? So I will touch on two problems. There's way more. Two problems. One is cluster management, right? So if you have a single box database, it can take, it will be up for 5 years. Once every 5 years, it will go down. You will recover from a backup. You will have 1 day downtime. That's perfectly fine. If you have a 100 nodes cluster, one node will be going down every couple of weeks. So at that point, you cannot afford downtime. So you need some sort of cluster management. The way it usually would be done is some multi-tiered approach, where most of the nodes have no idea that there's even a cluster. They will be just storing the data they're responsible for and processing it. But there's going to be a few nodes which orchestrate the cluster. Among themselves, let's say it's 10 nodes, they need to reach a consensus about which data is actual, who is online, who is offline, which nodes exist, which do not. That is a significantly easier problem than maintaining a blockchain cluster, because there's no adversarial behavior. All the nodes are running binary you wrote. So the only adversarial behavior which is possible is some node actually being unavailable. And yet, most of the distributed databases lose data under stress. There's this incredible block. If you haven't seen it before, I would recommend going through it. It's called Japson. And in that block, they deploy product databases like MongoDB, VaultDB, Cassandra, and they stress them. And each and every one of them loses data under stress. So despite the fact that this is a significantly simpler problem, reaching a consensus among 10 nodes without adversarial behavior, nobody can properly solve it. The second problem is query execution. So this is less relevant to blockchain today. It will become relevant within a couple of years. We're going to talk about that today. But once you start sharding your data, now every node is only responsible for some subset of data. And so for as long as the query you run only uses data from a single shard, you're fine. Right, so let's consider an example. Let's say you have 2 tables, one is users, one is user orders. And let's say they sharded across 2 shards. And they both sharded by user ID. So for a particular user, his information and their orders are going to be on the same shard. In that case, if you want to execute any cross-shard query which touches both tables, they will be executed efficiently because the joins can be executed on each shard separately, and then you just aggregate the resulting data, which is usually relatively small. You can aggregate on a single machine. It all becomes way scarier once you start running cross-shard joins which want to join data on a key which is not a shard key for one of the tables. At that point, you need significantly more sophisticated processing approaches such as map shuffle map or MapReduce, which are not rocket science. MapReduce has been around for 15 years now, and yet very few, again, databases actually use it, and definitely not a single blockchain uses MapReduce today. And as I mentioned before, there's practically no transactional database today that supports cross-shard joins. There's Google Spanner, which is built by Google engineers, and there is TiDB, which is built on top of Spark SQL, which I don't know how many of you know Spark SQL, but Spark SQL is slower than putting all the data on a single machine and executing join in Postgre. So effectively, there's no cross-shard joins in transactional processing. There are analytical databases such as MemSQL that support it, but they are expensive and they designed for a completely different use case. So now on this optimistic note, let's move to sharding blockchains and how that is applicable. So today there's one practically used in practice distributed decentralized blockchain which supports smart contracts. That's Ethereum, right? So there are others. There's EOS, which is not quite decentralized. There are a few others, but there's one that is actually used in practice. That's Ethereum, and Ethereum is effectively a single box database in the sense that in Ethereum, every transaction is processed by every single node in the cluster, meaning that the entire system is as slow as a single node that operates the system. All right, so what people do to address it? Well, the most active effort within the Ethereum Foundation today is called Plasma, which is effectively, you would run a significantly less secure blockchain, which is way faster than Ethereum, and you will process transactions on that blockchain, and you have a secure way of moving assets between Ethereum and Plasma chain, which effectively works in a way that even if the Plasma chain operators are malicious, they cannot prevent you from moving your assets from the Plasma chain back to the Ethereum chain. So, to an extent, Plasma chain is memcached. It is a way to address scalability issue short term, which is not generalizable to all possible use cases, and it's achievable very short term. So most likely, Plasma will become used actively within maybe before the end of this year. Definitely next year, Plasma will be used quite widely. Then there are some other protocols that some of you might have heard about. I put two of them that I know, Thunder and Solana. I'm sure there's more being developed, where the idea is, well, let's put one very beefy server and process all transactions on that beefy server and find some way to make sure that that server is not behaving maliciously. And if it does, to kick it out and replace it. Right, so that is what scaling up effectively is in the past. In the past, you would buy a more expensive server, similar approach here. Again, it is a huge benefit of this approach is it is achievable short term. So Thunder promises to launch their mainnet until the end of the year. Solana promises to launch their mainnet until the end of the year. So we will see how that goes. But so the question is why not sharding? Well, again, because sharding is hard, and so let's see how sharding would actually be built and how it is. What challenges are there? The easiest way to think about it is if all we care about is speed, then let's go and just shard processing. So every node in the cluster now will not process all the transactions. Every node will process some subset of transactions. But still every node will store the entire state. So this way, if they need to read any information, that information is available. If they need to write any information with some smart way of communicating between nodes, they can also update any piece of information. That is not as challenging as sharding the entire system. And there are companies which build it. Zilliqa is one of the most famous examples of a company that builds sharding processing without sharding data. There is a big problem with sharding processing. This chart displays the size of the Ethereum state over time. And it is clearly a linear dependency between the size of the state and time. Right? And so as of today, not today, I think it's September 2018, it is 100 gigabytes. Right? And that is at 14 transactions per second. So if we want to scale the system to thousands of transactions per second, the state will grow to terabytes very quickly. Right? So that is, sharding processing is a very short-term solution. Well, then we need to shard state as well. So when we shard state, now each node is responsible for some subset of state, again, the same as it was in databases world. And every node only processes transactions that affect the part of the state that it is responsible for. So that is not how sharding state usually defined. Usually that, in sharding state, that is not a requirement, but it does make much sense to shard state and not shard processing. So we will assume that if we shard state, processing is also sharding. Now, at this point of time, most of the research on sharding state assumes that every smart contract will only reside on a single shard. Right, so contracts do not span multiple shards. Contracts do not span multiple shards. If you want to execute a contract, you find the shard it belongs to, go to the shard, execute the contract. And an example of a product that is building that approach is Ethereum 2.0 proposal, which is going to be sharding state and sharding processing. And I have this gorgeous diagram from Prismatic Labs that explains how sharding state in Ethereum works. Important here is that Ethereum does not want to fork when they switch to sharding, and so they keep their main net, which is a proof of work net, so it is not going to be removed from the network. However, it will not be used as extensively as today. It will primarily be used for people to propose themselves as validators in the remaining chains. And so all the remaining chains are proof of stake. And there are validators who participate in maintaining the remaining chains. Now, there's a large pool of validators, and a subset of validators processes every shard. So there are multiple shards. Each shard processes a subset of transactions and maintains part of the state. And a subset of validators processes every shard. There is a big problem here, which is, let's say we have thousands of validators that staked a lot of money, let's say $1 million to participate. For them to collude, they would have to lose something on the order of $1 million. Now, let's say we have 4,000 shards, and those validators are split across shards. Now someone would only have to lose something on the order of, how much? 2,500? Maybe even 10 times less. Yeah, so it's significantly smaller amount of money. Right, so each shard is significantly less secure than the entire network. So the way Ethereum addresses the problem is, in every shard, the transactions, after they process, a certain message is sent to a special chain called beacon chain. And the beacon chain actually has a larger set of validators with a larger stake. And the beacon chain reaches a Byzantine consensus on what is the state. And so now for the history to be rewritten, a very large amount of money needs to be lost by colluding entities. So now what is the problem with this approach? There's one problem, which is cross-shard transactions. Imagine that Alice and Bob want to transact. Alice wants to send money to Bob, and they reside in different shards. Alice is on shard 1, Bob is on shard 2. That creates a problem that maintainers of shard 1 cannot add money to Bob because that's not a part of their state, and maintainers of shard 2 cannot subtract money from Alice because that's not part of their state. So we need some sort of cross-shard communication in place. And at this point, cross-shard communication is an active area of research. And I don't think any sharding proposal has a full story of how their cross-shard communication will work. So I will just go through some proposals, which are not mutually exclusive. Some of them complement each other, but effectively what people were proposing for cross-shard communication. One of the easiest solutions, the one that Zilliqa will be using for smart contracts, says, as long as something is within a shard executed in parallel, if you need to execute any cross-shard transactions, halt the entire parallel execution, execute all the cross-shard transactions serially, and halt execution that is parallel. So that works very well if you assume that cross-shard transactions are extremely rare. And so most of the time you will be executing transactions in parallel. Occasionally you will stop the parallel execution and execute few cross-shard transactions. The second easy approach is we internally call it Beanstalk. It effectively says, well, let's not have any cross-shard communication. And specifically for payments, that actually works. We just say every participant has an account on every single shard. And if you want to send money to someone else, you just find a shard in which you have sufficient amount of money and send money on that shard. If you don't have any shard which has sufficient amount of money, you just get a subset of shards and send money on the subset of shards. So in the extreme case, you would have to send on every shard, then you get no benefit from parallelization, but that extreme case is supposedly rare. Most of the time, you will have one shard which has sufficient amount of money, so you get a lot of parallelization. There's one not well-known blockchain that uses it called Fleta, and but I'm not necessarily advocating for Fleta, but their paper is actually pretty interesting. It's very simplistic and provides an interesting approach to sharding. Then one of the Ethereum proposals is called merge blocks, where they're effectively saying they have a technique which, for two blocks on two different shards, can probably guarantee that either both blocks will be present in their corresponding blockchains, or neither block will be present in their corresponding blockchains. And so this way, when the merge block is created, the validators on those two shards can then load the state for both shards and execute any transaction which affects both shards by having access to the entire state. That proposal has many advantages, but the primary disadvantages it has is we cannot have those merge blocks for any particular pair of shards too often, because there's n squared pairs of shards. And so if we only have linear number of batches of validators, it would take order n iterations before the merge block can be created again. And the second disadvantage is that it only works for cross-shard transactions that affect at most 2 shards. So if we have any transaction which affects more than 2 shards, that approach doesn't work. And then finally, the most sort of obvious working approach, which probably is also going to be implemented somewhere in Ethereum. It's definitely the way that Plasma communicates to the mainnet, and it is not unique to cross-shard communication. It can also be used to implement cross-chain communication, where like Ethereum would be communicating to EOS. It's called receipts. Well, the idea is that if we want to execute a transaction which affects multiple shards or multiple chains, we execute the first step on one chain, create a proof that that step was executed and is persisted on that chain, send that proof to another chain or shard, and then that chain or shard executes the second step, knowing that it was executed in the first chain. There's a lot of implementation details here, right? What happens if the proof gets lost? What happens if the shard that executed the first step is entirely corrupted because every shard is less secure than the entire system, etc. But for the rest of this talk, we will be using receipts as the way to implement cross-shard transactions. And so here's a gorgeous drawing of how that works. If Alice wants to send money to Bob, Alice sends the transaction to shard 0, where she resides. On that shard, the transaction is executed that subtracts money from her. And then a receipt is created with the proof that that transaction was executed. It is sent over to shard 1, where the validators of shard 1, having that receipt, execute the second part of the transaction and add money to Bob. Now, if it gets lost, as long as the receipt was created, Alice can resend it again. So that's the general idea. Now, with receipts in mind, let's see how sharding can look a couple years from now. So let's talk about sharding smart contracts. So in all the approaches we discussed so far, and in all the approaches proposed today, each smart contract belongs to a single shard. And that is more than enough for today. In today's world, the most used smart contracts, such as CryptoKitties or online exchanges, have between 500 and 1,300 active users per day. So at that scale, a single smart contract can easily live on a single shard, and it can scale up 2 orders of magnitude and still probably be able to live on a single shard. But at some point, I envision a bright future in which everything I have on my phone is running on blockchain, and not a single large corporation can steal my data. And once we move to that bright future, a smart contract cannot live on a single shard anymore. Right? So if we have a Twitter running on blockchain, it cannot live on a single shard. Right? Or if we have ride-sharing app living on blockchain, it cannot live on a single shard. So at that point, again, people would either have to build some hacks, such as using Plasma or sharding manually, or a blockchain can just support cross-shard smart contracts. So let's see how it can look. So first of all, let's assume that receipts are actually available as a primitive. So let's assume that all the problems that exist with receipts are solved. And what we do now is that the state of the smart contract now will be sharded across multiple shards. And so we will talk about a few approaches today to implement that. It's tail calls, scatter, collect, and MapReduce. So first, let's talk about tail calls. And we will use Uber as an example. Let's say we want to build Uber on blockchain. And that's, that Uber scaled up, scaled out, and now nothing fits on a single shard. So we would naturally want to have some information about cars which are available at this point, and that will probably be sharded by car ID. Because if you want to update any information about the car, that's the only way to find it. At the same time, if I'm calling an Uber from my phone, I need to quickly find a car in location near me. So there's got to be some index on the cars that is sharded by location, so that I can quickly identify shards which are responsible for particular locations and find cars which exist in that shard. Right. So let's say now a car is driving through the city. So let's say we consider Berkeley. We split Berkeley into grid of somewhat largish location chunks. Let's say it's like 1 mile by 1 mile. And so as car is moving, it will be crossing boundaries of those location shards. And as it crosses the boundary location shard, we want to update it. We want to move it from one shard to another. So the way it would look is, on the left, I have a Python implementation with some fake API of how it could be implemented in principle. We would want to move a car to a specific new location. We will identify its present location, remove it from that present location, add it to the new location, and change the location for the car itself. The problem with this function is that each of those 4 lines can, in theory, require to be executed on a different shard, right? And so if we want to use some general purpose language for writing smart contracts, we would have to use reflection at a very, like at extreme capacity to actually split that smart contract into multiple lines, execute them separately on different shards. More importantly, the problem for developer here is that the developer can accidentally create a smart contract which will involve a lot of cross-shard communication without understanding it. Right, and so here on the right, I have an example of how that would look, right? So the car resides on shard 0, the old location is on shard 1, the new location is on shard 0. So the contract will start on shard 0, update the car, move to shard 1, update the location, move back to shard 0, update the location in the car. So the way to build it in a way that it is more obvious for the developer that they having some cross-shard communication, and is also significantly easier for the system to split the code into individual chunks, is to use what is called tail calls, or it is also known as continuous passing. Continuation passing, thank you. Where effectively what we're saying is there's one function which is the entry point. In this case, it's move car. And what it does is the first argument is what it is sharded on. So in this case, the first argument is car ID. So the car ID is what will be used to determine the shard. It will go to the shard for that particular car ID. And the entire body of the function will be executed on that shard. So the developer needs to understand that only data that resides on that shard is available to them. And once they want to move to a different shard, they effectively invoke another function, passing as the first argument the shard key for that other function. And they are only allowed to call that function as the very last instruction of the function. That's why it's called a tail call. Right, so in this case, to move a car, we will first go to the shard with the car. We will identify the location, and nonce is just a way to prevent some race conditions. And then the second step needs to be executed on the shard of the car. So we invoke a function that will perform the second step. And the second step identifies, performs some operations to avoid race conditions. And you can see that both if and else, as the last instruction, the body of them has another function call, which will go to another shard. But importantly, both of them would be the very last instruction of the function. All right, and so the way it would look ultimately is on shard 1, we would call move car. So left to right is time. We call move car on shard 1. It executes the body that needs to be executed on that shard. The last instruction is the tail call to remove location, which goes to shard 2, where the location belongs to. It is executed there, and as a tail call, it goes to add location. Now that simplifies it significantly for the system, because extracting individual functions is very simple in most of the languages which have reflection. And for developer, it is very clear at which point the cross-shard communication happens, and they can easily see how many of those jumps will be performed. Okay, now the second, so tail calls works very well for as long as at every given point of time the smart contract wants to be executed on a single shard. Now let's say that at some point we want to execute the smart contract on multiple shards in parallel. An example of that is me calling a cab in Uber. I belong to a specific mile-by-mile location, but I could be at the very boundary of it. Right? So as I'm searching for the car, I probably want to look at all the locations around my location. So without loss of generality, let's say we want to look at the 9 locations which surround me. And so the idea is that, let's say I belong to shard 1. That's where my user ID is located. And as I call the car, it goes to 9 locations. Some of them belong to shard 0, some of them belong to shard 1, some of them belong to shard 2. And so it will scatter the calls to those shards. In each shard, it will execute some code, and then ultimately, all those shards will gather back again together to my shard, in which the final processing will be performed. Now, the problem with that is that, so scatter is actually very simple, right? If I want to call 9 instances of a single function. I'm just sending a receipt with the proof that the first step was executed on my shard to all 9 shards, and each of the 9 shards will just execute the step. Gather is a little more complex because at this point, let's say shard 0 executed the step faster than everybody else, and they sent back the receipt to shard 1. Shard 1 cannot execute the following step yet because they need to accumulate all the receipts from all the shards. The beauty of scatter collect is that when we scatter, we know how many instances of the function we're calling. Like in our case, it's going to be 9. And so gather knows how many receipts it is expecting. Gather knows that each of them needs to send back the response, so there's going to be 9. And so the validators in the shard that is performing gather, or rather collect, they will wait for 9 receipts, and once they receive all 9, they know that they can continue. So here I have an example of that function, FindCar. So at the beginning, user ID is looking for a car. We identify their location. We build a list of all the locations around them, and we call scatter to call the next step on all 9 shards. And then the second step is the actual function which will be executed in all of the 9 shards, receiving one of the 9 locations, which finds the closest car using some convenience function, and then it sends back using call to collect the information it computed to the single shard, and on the single shard it gets all the cars, chooses one which is the closest, and returns it to the user. Right. So the way it would look is, let's say the user belongs to shard 2, the user calls FindCar, and then there's 9 FindCar internal which will be executed on the next timestamp in multiple shards, and then on the third timestamp they all send information back to one shard where the last step is executed. So that on itself is already a pretty powerful execution framework. For example, in Google, a lot of things are implemented on top of BigTable, and BigTable effectively only allows you to change one row at a time without any locks, and a lot of products can be built on top of it. But ultimately, it still has quite a few challenges. Challenge number 1. Let's actually look at how receipts work in Ethereum, or how they could work in Ethereum in the future. So let's say we start some execution in shard 1 on the very first block. We do the execution. Now we want to send the receipt to another shard. Before we can send the receipt, the transaction needs to be finalized, right? For another shard to be certain that the transaction has happened, that transaction should become irreversible. So in Ethereum, that means that that transaction needs to be cross-linked to the beacon chain. The beacon chain needs to make a one iteration of a Casper consensus. And then after one iteration of Casper consensus, where the block is final, that needs to be sent back to another shard, which will be doing the execution. Each of those steps takes quite a bit of time. Each shard chain publishes blocks every 8 seconds. So we're looking at least for 8 seconds before it even gets cross-linked. Casper consensus is not instantaneous. It's quite a few validators reaching a Byzantine consensus. It's a slow procedure. And then it takes another 8 to 16 seconds to get back to the other shard. So we're looking at 30 seconds to a couple minutes per one cross-shard communication, if we're using this approach in Ethereum in a naive way. Right. So some other approach needs to exist. I don't know exactly what Ethereum is planning to do, and I think that is not their present focus. Right now they're mostly building the beacon chains. Cross-shard transactions are yet to be figured out. That's my understanding. So what we do is we build a technique called TXLow, which we will post on Ether Research and on Medium within hopefully this week, next week at the latest. So stay tuned. That will be published soon. Then challenge number 2 is concurrency control. So in my example of Uber app, that particular code, if it was actually working, would have a lot of race conditions. So the way it is built, it would probably not work, right? And very often you need to make some decision in one shard based on some data in another shard, which can change as you're making progress. That problem has been researched extensively in the databases world. There are multiple approaches. There's a pessimistic concurrency control in which if you have some data which you depend on, you just lock it and you prevent anyone from changing it. That has a lot of problems in the blockchain world. if you log some data and then you disappear, validators collude or anything, that data is unavailable. There's an optimistic concurrency control in which you execute the entire function assuming data did not change, and then you check if it changed. If it changed, you're like, well, that's unfortunate, and you start from scratch. If it did not change, you commit. There are some other more sophisticated approaches. One of them is used by a database called VaultDB, where they serialize all transactions and have a lot of heuristics to make sure that does not become a bottleneck. Ultimately, I think the most promising approach for the blockchain world, that I think is what Ethereum is planning to build, that is what we most likely going to be building, is if you need to have to process data from multiple shards in a way that requires concurrency control, you temporarily move all the data to a single shard, process it in a single shard, and then you distribute it again. Then finally, scatter collect that I showed is it's a subset of a more general framework called MapReduce. And MapReduce it enables significantly more powerful use cases. However, in a blockchain, in a naive approach that I presented, it would not quite work, because in scatter collect, the huge advantage was that by the time we collect, we know exactly how many receipts we are expecting. Right? If we scattered 10 instances of some function, we're expecting 10 receipts when we collect. And MapReduce in general, every particular invocation of a function can scatter more. So you know, at the beginning you call map on 10 partitions, that can call map on 20 partitions, etc. And reduce or group by in general does not have to go to a single shard. So it could be that as we group by, those the data is sent to multiple shards and aggregated on them. So in this example, I have here the reducer on the very last step sends 3 receipts to one shard and 2 receipts to another shard. So at this point, some sort of orchestration is required to keep track of what is happening across the system, how many receipts to expect in every shard, and how to execute it. Cool. Okay, so that I guess concludes the talk. We have quite a few people here from NEAR, so if you want to learn more about us, just find anyone.